Hello YouTube! Are you interested in modeling the price of gold using signal processing? If so, stick with me. Okay, so in the last video that we did, we used least squares in order to model the price of gold, and what we got was an exponential curve to follow the price of gold since 1973. All right, I'll show you that just to remind you, but if you haven't seen my last video on the price of gold, I suggest you check it out because that's a very useful tool, and it's part of this series on modeling the price of commodities using mathematics. This is a Mathematica tutorial on modeling price. Okay, so this is what we constructed in our last session on the price of gold using a technique known as least squares. So we constructed this exponential model and we got an equation for it. But now as we proceed to do more on this to get a better model for the price of gold over the last 45 years, well, what we want to do is first of all fill in the missing days in the data, right? So down here I've got the comment, the data has missing days. So what I mean by that is, so we've got a price of gold for the 4th of January 1973. I think we had one for the 5th of January 1973, but not the 6th, for example. And because of weekends and so on, there are lots of gaps in the price of stocks, commodities, Apple shares, for example, and so on. So I'll show you one way you can fill that in order to do signal processing on price data. Okay, so first of all, let's have a look at how to fill in missing days. And so basically, I've got a little piece of code here that you could copy out. And I'll just tell you what it does. So for the gaps in the days where we don't have a price and we don't have a day, for the weekend, for example, what I've done is I've just carried the previous price forward until we have a new price, say after the weekend. All right, so that's what this code does. It sets z equal to the difference in the day, all right, minus another 1, and then there's an if condition. If that equals 0, then put the next point in the sequence, and otherwise do some other things. Okay, so I'm not going to talk about that. It's just a simple piece of code for filling in some missing days and replacing those empty positions with points consisting of a day and the price while it still was, say, before the weekend. Okay, so that's that. And then because I had to make a list for the gaps, I then flatten it out, so I get rid of the set brackets inside, and then I take the whole list and break it up into pairs again, and that's how I get a list of points consisting of all of the data plus the missing days. All right, so now that we've got that, I will shift this over and I'll open up a new notebook, file new notebook, put it over here, and we'll increase the magnification to 300. All right, so now I'll copy this over and I'll press Shift Enter. Shift Enter. Okay, that executes quite quickly, as you can see. All right, now you might want to have a look at that data. So let's evaluate n, the length of this new list, and let's plot the new list. Okay, Shift Enter. All right, so what this is telling me is that the original length of the list is 12,957. Okay, so and then now we obtain a list of length 16,802. That's great because that is roughly the difference in the last Julian day of the list, the difference between that and the Julian day of the first day in the list, 1973, the 4th of January. Okay, so that's exactly what we want. So we now have a list of this length. Now let's look at our plot. All right, so this looks a lot like the other plot, except now we simply have some extra points filling in the gaps. Okay, so we fill it in the weekends and everything else that was missing in that data. All right, now that we have that, what we want to do next is, let's have a look. All right, so I'll write down my comment. What we want to do is construct a list of pairs containing the day and the difference. So price minus the model. Okay, now we already did this in the first session on the gold price. And if you remember, what we got is some positive values and some negative values. So when the price is up here, say in a bubble above the exponential curve, that would be positive, and then down here in the dip, the price would be negative once we do that. So I'm redoing that. The only difference here is that I'm doing it with this new list, which we've called WW. All right, so I'll copy that out and I'll paste it here. I'm not writing this out from scratch because there's quite a lot of code here to do today, and I want to move through this in, say, a half an hour or so. Okay, so now I'm calling double N. NN is 16802, right? The new length of the list. And now this H is this difference we're talking about. The difference between the price of gold and the exponential price model that we constructed using least squares in the last session on gold. Okay, so this is WW, the jth element, but the second element because those are pairs. So that's the price on the jth day, minus our model, which is right here, this exponential function, and it's got this this line in the power of e. Okay, that we again found with least squares. All right, so let's press Shift Enter, put this into memory. Okay, now it's into memory, and now we can list plot that. So list plot. All right, and this is what that looks like. Okay, so the horizontal line basically is on the exponential curve, right? So anywhere above that exponential curve that we constructed, you might think of as in a bubble, and down here below is a dip. And so you would have been wise to buy gold around that time to ride this up to the top and then sell and make some bucks. Okay, so now that we've plotted that, let's go down and consider our next. Let's have a look at a little bit of the data. So I've got the function take. So let's just look at the first 7 elements of this list and just check them out. Okay, here are the first 7 elements of that list. Now these are Julian days, right? And you can see they're all consecutive, so that's good. We filled in the data there. Okay, and yeah, that looks fine. They're points. Okay, now what we want to do next is take the second component. So excuse me. So I want to make a list of prices now. Right, and we will call that G. So I can put a semicolon around what I've just done, so to suppress the output, and then this list G will be long, so we don't want to see that. And then under here we'll just have a look at the first, say, 5 elements of G, just to be sure that things are coming out as we expect. Now that's a good practice because if you look at the data as you produce it, you minimize the debugging that you have to do later. Okay, so let's press Shift Enter and see this. Okay, now we have a list of just prices above the exponential curve, and you can see these are below it because they're negative. Okay, so that's good. That's what we expect. All right, now that brings us to the interesting part of this, which is signal processing. Now I'll just briefly describe what that is. If you have a sum of 2 periodic functions, for example, signal processing is the process by which you make a transformation, and what it does is it shows you those two periodic functions. So it shows you how to break apart a sum of two periodic functions or more into the individual signals, so the individual periodic functions that make that up. Okay, so I hope to be able to show you that in more detail. Now, that is a rather involved process, okay, that I will save the discussion of for another video, but there is a built-in function called Fourier that does this for us. Okay, so I'll paste it here. So Fourier, so I'm taking the Fourier transform, the discrete Fourier transform of this data here. All right, so G. I'm applying that transform to G, and I'm using the Fourier parameters 1 minus 1 that are appropriate for signal processing. All right, so next we want to have a look at the data. All right, so I'll take the first 5 elements and show us. All right, now these, you can see, these are complex numbers. So they have an imaginary component to them. All right, that's fine, that's what we expect. So there's a real part to this, and there's an imaginary part. This I denotes the square root of -1. Okay, so, which of course is not a real number. So these are not real numbers, they're complex numbers that are coming out of this. Okay, now that you understand that, let's put a semicolon and suppress that output. Next, what we want to do is apply filtering in the frequency domain. So if you watched my video on music, this came up, but I didn't actually do the filtering process. I just told you how you might do that. Okay, but I'm actually going to do this now. So I'll write the comment that we are filtering in the frequency domain. Okay, and next, when you do this, you want to choose a tolerance. All right, because you want to throw away certain frequencies that you're not interested in. Right, in our case, we want to throw away the little noise of the daily trades. All right, we'll just call that noise, and we're interested in the bigger swings in the data. So that's what we're doing now. Now I've set 40,000, that's just arbitrary. So you could choose your own, and we'll change this a little bit later so we can see how it affects what we're doing. All right, now the next piece of code constructs a list that does the filtering. So what this says is if the modulus of these complex numbers, now we have ABS because the absolute value the modulus of a complex number, meaning the distance of that complex number to the point 0, 0 in the complex plane, is a generalization of the absolute value. So in Mathematica, the command ABS does exactly that, and it works for complex numbers as well as real numbers. Right, so if the numbers are real, it takes the absolute value. If they're complex, it takes the modulus. So what we're saying is if the distance of this complex number is the distance to 0, 0, if that's sufficiently small, as in less than the tolerance, instead replace that complex number with 0. All right, so as in the real number 0, put the real number 0 there in its place. And if it's not less than the tolerance, we'll just put the complex number there. Okay, and so what we do is we tabulate that if command over all of the elements of the list. So we check that for every element, and then all right, so let's execute that, and then we'll consider the first few elements. So next, I want to show you the first 50 elements of this list of complex numbers. Now you can see not much filtering was done. You scroll through this, you do see a few places where there is a 0. So we did do some filtering, but not a whole lot, okay? So not a whole lot. All right, so now that we understand that, let's put a semicolon there so we suppress the output. All right, and let's move on. Now you might want to know what is the length of Z, just to check. All right, it's still 16,802, so that's good. All right, next, I want to apply a formula to this. All right, so we have constructed some complex numbers, replace some of them by 0, and next what we want to do is construct a function from this, which is a sum of periodic functions. I'll just write what that is, and I'll have to make this bigger so that it goes in one line, so it's a bit easier to see. All right, now this says the first complex number divided by the number of elements in the list. So we had nn for that. All right, and then plus 2 over n, and then this is a sum from 1 to the floor of n divided by 2, subtract another 1. All right, so we sum these periodic functions. So this is the real part of the kth complex number, and then that gets multiplied by this cos function. Similarly, there's a sine function and the imaginary part of the same complex number. All right, so that's the formula that I'm using, and you can actually prove that formula once you get to know more about signal processing. Okay, I'll leave it at that, and we'll continue on to do some calculations. All right, the next thing we want to do is construct this, the top of the sum. All right, so I've got m for that. M is the floor of n divided by 2, and then subtract 1. So we'll put this in memory. All right, that's 8,400. Okay, and then the two functions, the two periodic functions, once we multiply this inside, we would be interested in what I have called f and g. So that's these two functions. All right. Now you'll see here that I'm subtracting from t the first Julian day, which is the 4th of January 1973. All right, because one of the assumptions in using the tools of signal processing is that your data has its x-coordinate, or in our case, the t-coordinate, equal to 0 at the beginning of the data set. And if it's not, you meant to translate so that it is. Okay, so I'm just doing the translation right there. Okay, and next, we want to construct a list of all of those periodic functions. Okay, and I'll just copy that and paste it right here. Okay, so let me explain what that is. So I'm tabulating this right here, and what I've highlighted is just this inside the brackets. So I haven't summed this up yet. I've just made a list of these. Right, because this is the process of separating the sum of periodic functions into actual distinct periodic functions. Okay, so I've recovered those periodic functions and I made a list of them, but there are a lot of them in this case because the filter is not too discriminatory, let's just say. All right, so if I change the filter, I would get less functions and it would be easy enough to show. Okay, so now that we have that, let's say I have then prepended that list with 1 divided by n times the real part of the first element of this list after filtering. Now let's go scroll back and have a look at that, because I think we did take... All right, I'll unsemicolon that. Look, so basically this one is essentially a real number because this imaginary part is so close to 0 that it just is made up of errors in the calculation. So it's really just a real number. Okay, now the rest of these come in pairs. You might not be able to see the complex conjugate pair, but it is in this list somewhere, probably at the other end. All right, so we have minus 630,637 plus this imaginary part. It also comes with minus 630,637 minus this same number, but it's at the other end of the list. Okay, so now the reason I said that is because this one here at the front doesn't come with any pair, it just is on its own. Okay, so we have to treat it differently in this formula, which is why we have it here in the front. Okay, now that I have explained that, I'll put the semicolon back onto this, shift enter, and I'll come back here and show you the first 5 elements of this list, right? Which will tell you some of the periodic functions that the fluctuations in the price is made up of. All right, so here we see the first 5 of those, and there are quite a lot of periodic functions involved. Okay, now that we've done that, let's continue on to the next part, which is to take a sum. Okay, so I'll come down here and I'll write double F is the sum of the kth element of this array R, right? And we're going to take this sum from 1 to n plus 1. All right, now it's just going to be a sum of all these elements in this list above, and it goes on longer. All right, so now that we have that, let's plot it. Okay, so I want to call this plot double M, double uppercase M. So I'm plotting this sum, and I'm going to do this from the beginning Julian day, the 4th of January 1973 to a couple of days ago, when I first started this exercise. Okay, and I'm putting plot range all so we see all of it, and then we're going to show both of these together. All right, but actually I think we should probably show double B as well, because that was the list plot of the data. Okay, so I'll put 3 of those and shift enter and show it to you. Okay, so the first one is the sum of the periodic functions. Now that looks pretty much correct, doesn't it? All right, the second one, let's see, what was the second one? The actual data points, okay? So the similarity in these is uncanny. Now remember what these are. I'll remind you, this is just the difference between our exponential price model and the actual price, right? Because the price model that we constructed using least squares was an exponential curve, and then the actual prices were above and below that, right? So what we've done is model the difference between those prices using a sum of periodic functions, in other words, signal processing. Okay, now let's have a look, plotting the 2 of those together. Let's scroll down and see that. Okay, now look at this. The solid line is our model of this, and the dots are the points. So you can see that's a great fit. Okay, now that hopefully you're convinced that this technique is effective at modeling, okay, let's continue on and see what's up next. All right, now that we've got that, let's add this to our actual price model, and I'll go back. Can I go back and show you? No, because we've opened up a new. All right, okay, but I can do so on the other one. So all right, so I'll go back and show you that. Okay, so this is the model we previously constructed, this exponential curve. And right now what I'm going to do is add the periodic components on top of this exponential curve and see if we can replicate this with an actual function of t. Okay, so I'll take this back over, and then I'll paste the next piece of code under here. All right, so I'm calling this double Z. So this double F here, this is what we just did. It's just the sum of these periodic functions. And then this is our exponential model of the price of gold over the last 45 years. Okay, so double Z is that. And then we'll want to plot that. So under that, I'll just write double Q is the plot of this in the appropriate span of days, which covers 45 years. Okay, shift enter. Let's have a look. Okay, so here it is. Here is the model that we've constructed for the price of gold over the last 45 years. So it looks pretty accurate, right? Now the fun thing about that, let's just say fun, because you know, you got to be careful when it comes to predicting the future with mathematical models. They have limitations. But the fun thing about this is if we add, let's take this, plot another 1,000 days and see what happens. Okay, look at that. We've got some more chart. Okay, so let's take this to 5,000 extra days. All right, and now look at that. So what this is doing is it's just taking basically the periodic part of this end here, and it's continuing that pattern on, right? But what we've done is added it to the exponential function. So can you take this to be a good price prediction for the future? Well, the answer is definitely not, right? Not unless these peaks and troughs happened for a reason that will continue to happen. All right, so some things, some prices may have natural periodic components, say because some things are seasonal. Okay, so those might have fluctuations in the price for a good reason. All right, so when that is the case, then maybe you can rely on what you get from applying signal processing methods to your price models. Okay, so yeah, that's really interesting and fun, I think. Okay, now what happens if you take this 10 times further? Let's have a look. Well, now you don't even see the fluctuations, okay, because they're so minor. They're so minor that this now looks like the exponential function. Okay, so let's get rid of that and go back. And oh yeah, the last thing I wanted to show you is what happens when you adjust the filter. Okay, so let's go back here and adjust the filter. Let's see, where did we set that? Right here, tolerance. Okay, so if we make this number higher, then it will be filtering more things out, as in throwing them away. More frequencies will be thrown away and considered to be noise. All right, so let's choose another number. Let's just double it and see what this does. Okay, Shift Enter. Go down here and do this again. Okay, Shift Enter. And you can see this is a lot smoother now, right? Okay, so let's scroll down. Is it still a good price model? Well, maybe it is. All right, but if we really take this up higher, let's go 150,000 and see if that does anything. 150,000. So what I want to show you is the actual list double Z. It should have more zeros in it, and you should be able to see. Is this what I wanted to do? Well, I'll semicolon this out and have a look at this one, the take Z50. Okay, now it has a lot more zeros in it, as you can see there. So that says maybe it's better if I make this go higher to say 300,000. Hopefully we get even more zeros. No, not high enough. 800,000. Okay, more zeros. Okay, maybe that's good enough that we can then come down here and show you what this list looks like. All right, so here is the list, and so you have much fewer periodic functions in this list. Okay, so I'll put a semicolon on that, and then down here we will just say, what is union, right? Because union will throw out the extra zeros. Union R. Okay, and once we take the union, all right, once we take the union, we see that these are the most significant players. These 1, 2, 3 periodic functions are the most significant players in the big swings of the gold price over the last 45 years. All right, but it will probably be a bad model for price. Now, you might speculate as to what these big big functions are due to. All right, so I'll leave that to you. The speculation I'll leave to you. We'll just have another look at this plot. All right, you can see adding up these three periodic functions, there's not a lot of wobble in it, right? You can see it's just made up of 3. Okay, and there's our data, and then have a look. This gives a really rough model of that. Okay, and if we come down here and do this, yeah, this is a very rough model of the price action, let's say, over the last 45 years. Okay, well, that's all I have to show you for now. Thank you so much for watching, and I'm glad to say we now have 100 subscribers, so thank you for that. I hope you enjoyed this, and I'll see you next time. Bye.